Have you ever really thought about the copper in your phone or in the walls of your house? Where does it actually come from? Well, it starts its life as a simple rock dug out of the ground. Today, we're going to follow that incredible journey. We'll dive into the world of heavy and transition metals, tracing their path from raw ore all the way to the unique elements that pretty much power and color our entire world.
So, here's our game plan. First, we'll get to know what heavy metals actually are. Then, we're taking a super deep dive into the whole process of pulling pure copper out of the earth. After that, we'll see how that process stacks up against zinc and mercury, uncover the secret behind their awesome colors, and wrap it all up with a couple of key chemical ideas.
Okay, let's jump right in. First things first, what are we even talking about when we say heavy metals?
It all comes down to their address on the periodic table. See, if you look at that big central block of elements, chemists call it the D block, that's pretty much where you'll find all the heavy or transition metals. Simple as that.
Now, inside that group, there's this really famous little family known as the coinage metals: copper, silver, and gold. And yeah, the name pretty much gives it away. For literally thousands of years, these guys have been the backbone of currency, all thanks to their unique properties and, being kind of rare.
So what makes them so special? Well, they've got this whole suite of amazing properties. They're fantastic at conducting heat and electricity. That's why all our wiring is copper. You can hammer them into sheets and pull them into wires, no problem. They're also really dense and have high melting points. But chemically is where they get really cool. They have what's called variable valencies, which just means they can form different kinds of chemical bonds. This makes them incredibly versatile. And as we're going to see in a bit, that's what lets them form these stunningly colored salts and all sorts of complex compounds.
All right, let's get our hands dirty, metaphorically speaking. We are going to follow the complete metallurgical journey of copper, every single step, from a chunk of rock all the way to a 99.9% pure metal. The whole trip, from rock to pure metal, can be broken down into these 6 main stages. We start with the brute force stuff, crushing and concentrating the ore. Then we get into the really fiery chemical transformations, roasting, smelting, and bessemerization. And finally, it all wraps up with the very precise chemistry of refining. So let's walk through them. First up, you take these huge lumps of ore and just crush and grind them into a super fine powder. But then comes the really clever part, concentrating it. We've got to separate the good stuff, the copper sulfide, from all the worthless rock, which is called gangue. And to do that, we use a pretty cool method called froth flotation.
So check this out. It's all about some really neat physics. The powdered ore gets mixed with water and pine oil. Then you bubble air through the whole mixture. The tiny copper sulfide particles hate water but love oil, so they stick to the oily froth and float right to the top where they can be skimmed off. Meanwhile, all the unwanted rock gets wet and just sinks to the bottom. It's a brilliant way to enrich the ore before you start the real chemistry.
Okay, with our concentrated ore ready to go, it's time to turn up the heat. This is the roasting stage. The ore is heated in a special furnace with a ton of air. And the whole goal here is a critical chemical swap. We want to get that sulfur to leave the copper and bond with oxygen instead. This turns our copper sulfide into copper oxide and lets the sulfur escape as a gas. It's a huge step toward getting our pure metal.
And here's the special piece of equipment they use. It's called a reverberatory furnace. The design is so smart. The heat from the burning fuel doesn't hit the ore directly. Instead, it reflects, or reverberates off the roof and down onto it. This means you get all the heat you need without getting any of the ash or impurities from the fuel mixed in.
Next up, smelting. The roasted ore gets mixed with silica, which is basically just sand, and coke, and then it's heated to insane temperatures in a blast furnace. This intense heat melts everything, and the silica acts as something called a flux. It reacts with any iron impurities to form a liquid waste called slag. What's left at the bottom is the prize for this step, a molten pool called copper matte. And this diagram of the blast furnace shows you exactly what's happening inside. It's a fantastic use of basic physics, really. The lighter waste material, the slag, just floats right on top of the heavier molten copper matte. This makes it super easy to just pour them off separately.
All right, listen up, because this next step, bessemerization, is the main event. This is the chemical climax of the whole story. The molten copper matte gets poured into this big pear-shaped thing called a Bessemer converter, and then a blast of hot air is forced through it. This kicks off a powerful chain reaction that finally converts the last of the sulfides into nearly pure molten copper.
As all that last bit of sulfur burns off as sulfur dioxide gas, the gas creates bubbles that get trapped as the copper starts to cool. This gives the surface a really blistered look, and that's exactly why the stuff we get at this stage, which is now about 98% pure, is called blister copper. So we're at 98% pure, but for things like high-tech electronics, that's not good enough. We need to get even pure. The final step, refining, uses two cool methods. First is something called poling, where they literally stir the molten copper with poles made of green wood. The hydrocarbons from the wood react with and remove any last traces of copper oxide. Then, for the ultimate purification, we use electrolytic refining. This uses electricity to dissolve the impure copper and plate out 99.9% pure copper atom by atom, leaving every last impurity behind. So that was the epic journey of copper. But is it the same for every other metal? Not at all. Let's put a quick spotlight on two of copper's neighbors on the periodic table, zinc and mercury, and see how their paths are different.
When you lay it all out like this, you can really see the differences. Copper has that really elegant self-reduction thing going on in the Bessemer converter. Zinc, though, needs an extra push. You roast its ore, but then you have to heat it with coke to actually reduce it to zinc metal. And mercury? Mercury is the easiest of the bunch. You just roast its ore, which is called cinnabar, and the mercury turns straight into a vapor. You just cool that vapor down, and it condenses right back into pure liquid metal. The unique chemistry of each element really dictates its own special journey.
We've seen how we get these metals, but now let's talk about one of their most amazing properties. I mean, why are compounds made from transition metals, like that bright blue copper sulfate, so incredibly colorful?
It's a really good question, right? We all know table salt, sodium chloride, is just plain white, but copper sulfate is blue, nickel chloride is green. What is going on with the transition metals that gives them this whole artist's palette of colors?
The answer is buried deep inside their atomic structure, specifically in their d orbitals, which is kind of like where some of their electrons live. So according to something called crystal field theory, when a transition metal ion is surrounded by other molecules, chemists call them ligands, something really weird happens. The 5d orbitals, which are normally all at the same energy level, get split into two different groups, a lower energy set and a higher energy set, just like you see here.
And this is the key to everything. When white light, which has all the colors of the rainbow in it, shines on the compound, an electron can absorb a very specific amount of energy, which corresponds to a specific color of light, to make the jump from a low-energy d orbital to a high-energy one. We call this jump a d-d transition. So if the compound absorbs the yellow light out of the spectrum, the light that bounces back to our eyes is everything but yellow, which we see as blue. The amazing color we see is literally the leftover light that the electrons didn't eat for lunch.
Okay, to finish things up, let's just quickly clear up one final, really important distinction that always comes up when you're talking about these metals and the compounds they make. So what on earth is the difference between a complex salt and a double salt? This chart makes it super clear. Think about a double salt. When you dissolve it in water, it completely breaks apart into all of its simple individual ions. It just falls to pieces. But a complex salt is different. When you put it in water, part of its structure, this complex ion, stays tightly bonded together. It moves around as one single unit. That fundamental difference in how they behave in water is really the whole story. And that brings us to a final thought to leave you with. We figured out that the secret behind all these vibrant colors is those little electron jumps between d orbitals. So here's the question. Where else in the world, in chemistry or even biology, might you expect to find these colorful metal ions doing their thing? I mean, think about the deep red of hemoglobin in your blood, the brilliant blue of a sapphire, or the green of chlorophyll in a leaf. The story of heavy metals isn't just in factories and wires. It's literally everywhere, all around us, and even inside of us.